Hey you guys, here we go. We are going to learn about Riemann's sums, trapezoid rule. Let me go ahead and share my screen and get going. Okay, so the reason why we do these Riemann sums and trapezoidal rule is when we have an area of something, so we're given a graph or some data or something, and we don't have a function, so I'm not able to just take the integral and find that area. So in this case, I'm going to approximate rectangles. I'm going to make rectangles, and it's not an exact, it's approximation, and that will help me to figure out approximate areas. And then there's a couple of different ways to get closer and closer to the actual area, okay? So the first example, so let's say we have this, this graph right here, like this, and I want to know the area from 0 to 10. And the way that I show that is by an integral. So I have the integral from 0 to 10 of f of x, and I'm going to approximate this by adding the areas of the 5 rectangles. So see how there's 5 rectangles that would kind of, if I colored them in, it would be that area. And you can see that sometimes it goes over and that's not included, but then sometimes it's under and that's also should be included. So it's kind of an estimation, it's not exact, okay? So I'm going to find the area of each rectangle. So the area of this rectangle is 2 by 2. And the way that we came up with the 2 is we went into the middle of the interval and we found what that value was right there in the middle, and it was 2. So the area from 0 to 10 of this function is approximately 2 times 2, that's the first rectangle, plus 2 times 5, okay, because this goes up to 5, and I notice again that that's what the value was at 3, plus 2. So each rectangle has the same width, okay, they're all 2. This one goes up to 3, so 2 times 3, 2 times 1, and then the last one is 2 times 3 again. Okay, so I noticed that there's a 2 in each one because I kept my interval the same. So it's 2 times 2 plus 5 plus 3 plus 1 plus 3. So those were the heights of each of my rectangles. And I can add that up and I get 28. So notice the notation. This integral is approximately this, but this is exactly this, okay? So this is called a midpoint Riemann sum. Midpoint uses the height in the middle of the interval. Okay. All right, the next example says approximate this area by using 5 rectangles of equal width with an upper, which means circumscribed Riemann sum, okay? So this means it's going to be the rectangles are above the graph. The rectangles are above the graph. So I'm doing 5 rectangles and I have a space of 10, so that means each one's going to be 2, okay? So I'm going to go to here, right? But my upper point is right here. So I'm going to do this as my first rectangle, okay? So I'm going to come up to 4. So my first one, now we already learned, remember, that I can write the 2 and then the parentheses. This one has a height of 4. Okay, the next one, so in this interval, this is the highest, and that's 5. Okay, in the next interval, this is the highest, and that's 4 again. In this interval, this is the highest, and that's 2. And then the last one is the highest is right here, so 5 again, okay? This equals 40. So I notice if I use my upper, I have a lot more area that's not part of the actual graph. I'm just going to do these in different patterns so you could see the different rectangles. Okay, so if you use upper, sometimes it'll work. Like, can you think about a time when it would work maybe? We'll get that where you can kind of start looking to see what would be the best one to use, okay? And then we, of course, have a lower. And what do you think a lower is? We're going to use, instead of the above the graph, they're going to be right below the graph, right? Okay, so right here in this interval from 0 to 2, my lowest point would be 0. So my first one is 0. Okay, the height's 0. And then the second one, I'm going to go between 2 and 4. The lowest point is right here at 4. The lowest point here is 2. The lowest point here is 1. And the lowest point in this interval is 2. When I add those together, we get 18. Okay, so you can see the different ways that we can do it. So when we did the middle, we got 28. When we did the upper, we got 40. And when we did the lower, we got 18. On this graph, the middle would be the best because it is so up and down, right? So there's different times when you would use the different type, okay? So as your interval gets smaller and smaller, each of the methods gets closer and closer to approximating the same answer, okay? The bigger the interval, the harder it's going to be to get a correct answer, okay? All right, so now we're going to do another graph looking at this one, okay? And this will always tell you what type to do. So this is a midpoint Riemann sum. That's Riemann, you could say it however you want, okay? So it's 3 equal subdivisions. So I first have to figure out if this is like n equals 3, okay? Because there's going to be 3 triangles, one here, and one here. So they're going to have equal width. So each width is going to go 2 units again, okay? So I'm going to figure out in this interval, the middle point would be 1. So I need to know the function value at 1. I need to know the function value at 3. And I need to know the function value at 5. Okay, so yeah, I could do this integral and figure this out, but we're going to do it using a midpoint Riemann sum instead. So if I plug a 1 into my equation, I get 1 plus 10 is the square root of 11. Okay, if I plug a 3 in, I get 9 plus 10 is the square root of 19. And then if I do 5 plus 10, I have 35. So the square root of 35. Okay, so basically what I have is when I'm doing this area, I've got 2 times root 11 plus root 19 plus root 35, and I'm done. I don't have to do anything else. Okay, I'm not going to try and simplify that. The next one we're finding the area of this one using an approximation, okay? So I'm going to figure out, it tells you which x values. So this one is going to be -10 to -4. So my width on this one is not equal. Okay, so I'm just going to have to figure out what the width is between -10 and -4. So there's 6 spaces, right? So it's approximately, the first rectangle would be 6. And then I'm plugging in the middle of the 6, right? Okay. And this actually is telling us to use a right hand. So right hand means that of that interval, so I've got a -10 and a -4. That value is going to be the -4 value because that's on the right side. So I'm going to plug a -4 into my graph. So we get 2 to the -4 minus 8. So that's going to be the first rectangle. The next rectangle goes from -4 to 0. So 0 is on the right, so I'm going to see what the value is at 0. 2 to the 0 is 1, and then 1 minus 8 is -7. But I don't have to figure that out. I can just say 2 to the 0 minus 8. Okay? And then I'm going to continue that same pattern. 0 to 2 is 2. My function value at 2 is 2 to the 2 minus 8. 2 to 3 is 1. Okay, so we're going through and we're plugging each of those in. So 2 to the, let's see, we're plugging a 3 in on this one. And then the last one is from 3 to 5, so that interval is 2 spaces, and then I plug the 5 in because it's on the right. Okay, so that would be my using a right-hand rectangle. So if I have a rectangle like this, I'm using this height. So it's pretty close on this one. It's not, it's when you're going to get more to, like if I'm looking at 5's right here. So my rectangle is going to go up to here because I'm using the right hand. And that's from 3 to 5 would be this area. Okay. Okay, so now what we're going to do is the same thing, but instead of using a rectangle, I'm going to use a trapezoid. Okay. So first of all, the area of a trapezoid is just like a triangle, right? So a triangle is 1/2 base times height. So I'm going to do 1/2 height times base, but instead of the base, I have 2 bases. So I have to figure out what that base is. So 1/2 height and then B1 plus B2. Okay. So when we look at this trapezoid right here, the base is this and this. Okay, these parallel lines right here, the parallel lines are your bases. Did I write that? So the parallel lines are the bases. So here I'm going to have 0 to 10, f of x is approximately, okay, the first trapezoid, 1/2 times, from here to here is 2, okay, and then base 1 is 0, and base 2 is 4. So that'd be that first trapezoid, number 1. Okay, then number 2 is going to be 1/2 times, this one goes from 2 to 4, right, or actually 2 to 5. So this is 3, and then this base is 4, and then this base is 3, so 4 plus 3. Okay, and then we're doing the next one, number 3 is 1/2. This goes from 5 to 6, so times 1. And then our base is 3 plus 2. And then the next one, we have 4, for 6 to 8 is 2. And then on this, if you look at it, we're looking at the 2 bases right here and right here, they're equal, right? So they're both at 2. And then the last one is 1/2 times 2. And then we've got 2. And then this one is 1, 2, 3, 4, 5. And that would give us the area using that curve using the trapezoid. Okay, so what we're finding is that I can make these geometry shapes that are close to the graph to figure out what the area is under the curve. Okay, so this says use 4 trapezoids of equal width to find an approximation of the area under the curve y squared equals, or y equals x squared. Okay, so y equals x squared. I'm doing, I'm starting at 0. My next spot would be 1. If I was at 2, my next spot would be 4. Okay, so this is what the graph would look like. And I want to find this area under the curve between 0 and 2 using 4. Does it say 4? Why am I thinking 4? 4 right here. So since this space is 2, I'm going to be cutting this in half, right? To get those 4 trapezoids. Okay. So this one's kind of just like this, and then this one is like, we're going to connect this to this, so it's like that. And this one, we connect this to this, so it's like that. And this one, connect this to this, so it's like that. Okay. So it is a trapezoid. It is really following that curve pretty close. I'm betting that this is a pretty close estimation. Okay. So I'm going, it says I'm going to sketch the curve and draw the trapezoids first. So I just did that. And I could do these in different shading so that you can see the different ones. Okay. So now I'm going to do the first one, goes from 0 to 1/2. 1/2 times 1/2, and then the first base is 0, and the second base is, well, if I plug 1/2 into x squared, I get 1/4. So that would be the first one. And then the second one is 1/2 and 1/2. So now I'm plugging in the 1/4, and then I'm plugging in 1, which I get 1. So 1/4 plus 1. Okay. 1 plus 9/4. 9/4 plus 4. Okay, so this is going to give me my approximate area of that trapezoid. Okay, and what we find out is I can write this as 1/2 times 1/2, because that's on every single term, right? And then I'm going to multiply that by, well, I notice there's a 0 here. So I'm going to write the first number first by itself. And then I see there's a 4th here and a 4th here. So I'm going to do 2 times a 4th. Okay. And then I notice that there's a 1 here and a 1 here. So 2 times 1. 2 times 9/4. And then the 4 at the end. Okay. So I can simplify it by saying I just have to find the height at each value. So the height at 0 was 0. The height at 1/2 was 1/4, and I'm going to double that. The height at 1 was, or the height at 2 was 1. And we just keep going through and we find, like right here, this is the height, the height, the height, the height, and the height, right? But this one was doubled, and this one was doubled, and this one was doubled. So that's going to work for every trapezoid. So we come up with the trapezoidal rule by following this pattern. It's a fast way to do this. So this is the formula. The integral from a to b, so a to b of f of x is 1/2 times the width. That was our bottom width, okay? And then we do the first height, and we double all the heights in between until the last height, because the first height and the last height are not doubled, okay? The first height and the last height are not doubled. Okay, and I noticed that from when I did my trapezoid here, okay? Grab my paper back real fast. So I noticed that here. So my first height is 0. I don't see 0 again. My next one's a 4th, and I have a 4th and a 4th. So that one's doubled. And then I have a 1 and a 1, so that's doubled. And then we have a 9/4 and a 9/4, so that's doubled. But the 0 and the 4 on the outside are never doubled. They're on their own. So that's why we don't double the end points. Okay? So this is our trapezoidal rule. And that's for anything that has equal width. Okay, this won't work if they're not equal width, because then I can't put it right here out in the front if it changed every time. Okay, so it's only if we have equal width. So then we're going to do a couple of examples where we are going to write out the trapezoidal rule. Okay, so use the trapezoidal rule with 4. So n equals 4 equal subdivisions to approximate the area shown. So sometimes it'll break it up where you can see the 4 widths, and sometimes you'll know the distance and you have to figure that out, okay? So I'm going to say from 10 to 50, okay? The area or the integral under the curve is approximately, so I always have the half because that's my trapezoid formula. And then I need to figure out what the width would be. And on this one, it gave it to us. It's 10. Each one is 10 apart. And then I have to write the first height. Okay. So the first height is 1.8, and I can look at it right here. So at 10, it's 1.8. And then each of these are going to be times 2. until the end. Right? The first and the last are not doubled. So 1.8 plus 2 times 2 plus 2 times 2.5 plus 2 times 3.5, and then plus the last one, 2.2. That's what our area will be. And look at that. We don't have to do anything to finish that up. Okay. All right. That's it for the assignment. So now we just have this last page that tells you as your subintervals get smaller, the three methods approach the same number. Okay. All right. That's all I have for you guys. Let me know if you have any questions. Okay.